Hello everybody and welcome to today's video on how deep learning works. Last week we spoke about, or I released a video about how AI, specifically machine learning, works. And so let's get right into how deep learning works. So this is one of my favorite topics in AI. So let's get right into it. So from last week, we know that deep learning is a subset of machine learning. So subset, let me write it here, subset of machine that uses neural networks to analyze data. So it uses I'll explain all this in a bit. Analyze data. So neural networks, you might have heard of neural networks in the brain. So it's called artificial neural networks. Let me actually include that here. So artificial neural networks. So the artificial neural networks are inspired by the neural network in the brain, by the neurons, how neurons work in the brain. But the key word is inspired, because just imagine this analogy of how a paper airplane is inspired by a real supersonic jet. That's the same way artificial neural networks are inspired by the biological neurons in the brain. So it uses, now artificial neural networks uses a series of layers. As you can see here, I've already drawn some layers here. So there is the input layer, the hidden layer, and the output layers. So it uses a series of layers to analyze data. So let's get right into explaining all this here. So what is an input layer? An input layer, as the word input, it is the first layer in an artificial neural network. It receives the data. So for example, if we're building a model for maybe predicting the breed of a dog, for instance, so we will feed this input layer, receives the data, receives the images of these dogs, but it receives it in numerical format. So for the breeds of dog images, it would convert it into pixel values. So the RGB, so like example, black will be 000, white will be 255, 255, 255, and so on. So that is what this input layer receives, the numerical representation of the data. In this case, we're talking about images of dogs, dog breeds, so it's received a numerical representation of the data. So this hidden layer, as you see that I put this in brackets, it is usually more than one layer, but because of the enormosity of drawing more than one layer, I just stuck to just one layer here for the hidden layer. Please permit me to do that because it's a little bit tasking to draw all these things. It took me a while to draw this. So now the hidden layer is actually the layer that does the heavy lifting. It's the layers that in reality we have. I can imagine like this ChatGPT and those big AI tools with the big architectures, they have thousands to millions of hidden layers. So this one layer here, multiply it. So I want you to have that analogy as I explain. So this hidden layers does the heavy lifting. It learns the patterns from the data that was received from this input layer sent to it. It learns the patterns. It adds some computation to it. I will explain that next. I just want to give a background explanation. So it adds some computation to it, and then it sends its interpretation or the new transformed look of the data that it's worked on to the output layer. And then the output layer does the final computation before giving you the output. So in the example I gave you, for example, we want to just work on two types of breeds classification. We call it binary classification. So we want our neural network to predict if the image of the dog I feed it with is either, let's say, German Shepherd or Bulldog. So it would tell me if it's Bulldog here, it tells me maybe the probability of it being a Bulldog is like 0.99. That is super sure. And the probability of the image of the dog being German Shepherd to be 0.01%. Right. Okay, so after this theoretical foundational background, now let's get into how it really works. So let me use, what color do I use? I use blue. Let me use green. So now in this case we're using our breed, so let me specify. So already we're trying to predict or create, so that you have this in mind as we go, create a neural network for binary classification. We feed the input layer with images of dog breeds and desire the output here to tell us whether the image is a German Shepherd or Bulldog. So that is what we're trying, that's the neural network we're trying to create here. So now the input layer receives the images of these dogs. It receives it in numerical format. And then, now let's start with this first layer. We see that this arrow goes from this input layer all the way to this hidden layer, as well as from this to this. So every single one of this is called a neuron, artificial neural network. So one of this big circle is called a neuron. Maybe I should put this So one of it's called a neuron. So every neuron is connected to the next neuron in the next layer. So every neuron in a layer is connected to the other neurons in the next layers, but not within themselves. See, if you look at it, there's no connection between neurons in the same layer, but there is connection between neuron in one layer and the next layers and the next layer. You can see. So now once this input layer sends the pixel, so now we say that this input layer receives the numerical version or representation of the data, and we're talking about images here, so we're talking about like pixel values. So each dot here represents a pixel, and for example, maybe although realistically an image cannot have like 4 pixels, but let's just say for example we have images of 2 by 2 pixels, so that'll be 4 pixels in total. I'm oversimplifying this, just stay with me. So 4 pixels represented by 4 neurons. If it was 25 by 25 pixels, now we'll be talking about like 625 pixels, so that's 625 neurons. But because we don't have 675 neurons here, so let's just say we have 4 pixels of the data, so representation of the data. So these are the 4 pixels being represented by the 4 neurons. So this neuron that has the first pixel sends the data to the next neuron in the hidden layer, and also does to this one, to this one. So every neuron here is connected to the hidden layer. But what are these dots here? So these dots here represent the weights. What are the weights? Looking at the, let me use blue or red, weights. Weights are the importance placed or given to a neuron, or given to, let me even specify this further, given to the information a neuron carries, or a neuron. I'm just trying to be as clear as possible. Importance placed or given to a neuron, or the information a neuron carries. Let me just be as specific as possible, just to be so clear. Importance placed or given to the information a neuron carries. Information or feature. Let's say these are the weights. The dots represent, let me just put these dots here, hopefully, so you can connect those dots, means the weight. There's a numerical value that represents the importance placed or given to the feature a neuron carries. That's the weights. So for example, this neuron from here to this other neuron, let's say it has a weight of 2. And then from this neuron to this neuron has a weight of 4. This neuron to still this neuron has a weight of 5. This neuron to this neuron has a weight of 6. Okay, so we have one more thing we have to do. So the weights, when we get here, we have to add a thing called bias. But before then, you know that all these neurons, they have a numerical representation, right? So if, for example, the numerical representation, the number of the pixel, that's the numerical representation, the pixel value is, let me just give it a number of, let's say 0.1. Let's call this 0.3, 0.4, 0.2. We're going to, let me use white. So now for neuron 1, let me call it neuron 1. I don't know if I should be using white if it will show on my clothes. So let me just use blue. So neuron, I'm talking about this now. This is neuron 1 equals 0.1 multiplied by its weight. Then you do same for neuron 2, 0.3 multiplied by 4. Same for neuron 3, 0.4 multiplied by 5. Do the same for neuron 4, 0.2 multiplied by 6. Now whatever we get is what is called the weighted sum. So I brought my phone for a calculator. Calculator. To just make all of this faster. So 0.1 times 2, 0.2 0.3 multiplied by 4 is equals to 1.2. 0.4 multiplied by 5 is equals to 2. 0.2 multiplied by 6 equals to 1.2. All right, so this is a different color. It's called the weighted. We're going to add all of this together to get the weighted sum. Well, even before I say that, we're going to let me just specify what I did here in writing. So I said the value of the neuron multiplied by its weight. That's what I did here. So now, finally, do I make this bigger? Is this big enough. So I clean it and make it bigger. I hope you can see it. Let me just make this bigger. Value of the neuron. By its weight. And you know that all of this, so we're just even focusing on just one of this neuron, but this is what happens to all the neurons. So now all of this is then added together. The result of all this is added together. So let's add it together. So that'll be 6. Let me write this in red. Oh, orange. 6.34. 4.6. So this is what we call the weighted just right here. Weighted sum of inputs. Let me write this on in one line. Just trying to make it as clear as possible. $4.6. So I hope you're still tracking with me. So this weighted sum of inputs, 4.6, is now a value called bias is added to it. So let me explain what bias is. If you are into music, a weight is like the individual volume. If you for a music mixer, a weight is like the knobs for the individual volume of instruments. For each instrument, they all have their volume knobs on a mixer, on a music mixer. So the bias is the overall or the chief volume for everything. So if you turn that entirely down, you can, no matter how loud the individual volumes on their individual knobs is, you can't hear it. So bias is a value added or subtracted to the weighted sum of inputs that either increases or decreases the value of a neuron. By increasing or decreasing the value of a neuron, it increases or decreases the sensitivity of that neuron to the data. So now this bias is, let's say for example, the bias is let's just come up with a number and just call it 3. So we have to add 4.6 to the bias. So plus Let me use a different color. Blue. Use this plus bias, which will be 4.6 plus 3, which will be 7.6. Cool. Well, hold up. We're not done yet. So we're doing all of this. We're focusing on one neuron. This is what happens to every neuron, every connection. One more thing. So before the value of this, I wanted to clean the 3, but let me just leave it there. You understand from this. So once we get the weighted sum plus the bias, after all of this calculation, before the new value of the neuron is sent to the next layer, which in most cases will be another hidden layer, there's one more thing it has to go through. It's called the activation function. Let me use green color. The results of the weighted sum of input, which basically means the weight of the weighted sum of input plus bias. Okay, I'm writing it like this, plus bias has to go through an activation function. Okay, so what is an activation function? It has to go through an activation function. An activation function conducts a mathematical operation on the result of the weighted sum of input plus bias to decide if a neuron fires or remains silent. What does that mean? A neuron fires means that its value contributes to the next layer. A neuron does not fire or remain silent if its value does not contribute to the next layer. For example, if its value is 0, it doesn't contribute. So how does this work? A popular activation function is ReLU. Let me use orange. ReLU. ReLU stands for rectified linear unit. So how does ReLU work? If, for example, the result of the weighted sum of inputs, which is the weight multiplied by the value, the input, plus the bias. If for example we have 7.6, but if for example the value was 0 or a negative number, ReLU would output 0, and which means if the entire input, the value of this neuron is 0, it doesn't fire or it remains silent, in the sense that it doesn't actually contribute to the next layer. Even if the 0 value is sent to the next layer, next neurons in the layers, 0 does not contribute anything. But if the value is positive, like what we have here, it outputs the precise value, which is 7.6, and of course sending 7.6 over to the next neuron definitely contributes a significant value to the next neuron. So that's how it works, and basically this is how artificial neural network works. It works by adjusting the weight and biases. So this weight and biases were not the ones that selected. All we do is to select the model and we select the algorithm. Write it. We choose the model. For example, in this case, CNN, and the algorithm. CNN means convolutional neural network. It's used for images and videos. And with the algorithm, if you remember from last week, so a model is like a recipe. The algorithm is the steps, the processed steps, set of steps to actualize the recipe. Okay, so our model CNN, a convolutional network, we want to be able to classify if a dog is, whether the image is German Shepherd or Bulldog. That's convolutional neural network, and the algorithm is what the algorithm basically stipulates the parameters, such as the bias and weight. Those are parameters. We don't handle the parameters. We handle the hyperparameters, like the learning rate, the batch size, etc. But the algorithm, such for this kind of CNN, convolutional neural network, an algorithm we could use is stochastic gradient descent. So the algorithm is the one that works on the weight and biases, changes the values, reduces, decreases to ensure that the output is correct. So let me complete this sentence and then I'll explain more and then round it up. So we choose the model and algorithm. Or let's just say stipulates the algorithm for precise which are the parameters to help or ensure the model achieves its goal. So the way this works is initially when you feed your neural network with images of dogs, at the beginning the output will be rubbish because it's literally just testing, trial, test, error. So the weights begin with random values. The bias begins with random values and it just keeps on testing and testing. So initially the output is wrong, but as it keeps on learning, that's what learning basically is for an artificial neural network. It is literally just adjusting the weights and biases, adjusting the weights and biases, adjusting the weights and biases, adjusting the weights and biases until it's getting at least a good enough accurate output that says this image of a dog is bulldog or this is German Shepherd. So images of precisely two dog breeds because we're trying to use what we have here. And that's it. But this is just part one. The second part talks about how it corrects its errors. So when, initially when it outputs nonsense, how does it go back to correct all of these numbers? That's what they call back propagation of errors and how to fine tune your artificial neural network model for accuracy. So we'll do that next week. And I hope you understand. Please let me know your thoughts, your comments, and your questions in the comment section. Please subscribe for more. And thank you. See you next week.